Okay, so we have a short, snappy chapter here on what a mathematician would call graph theory, but you'd probably call network theory, something like that. Okay, now most of these notes are set up kind of it's kind of active learning. So what I mean by that is, you'll see what I mean in a minute actually, but it's kind of designed for collaborative tasks so that you'll learn in groups in the class. So obviously that's not possible the way I'm doing things. So what I recommend is that maybe you pause the video and try and spend 5 or 10 minutes trying to do the tasks. Now you won't be able to do all of them. Okay, so let's see what we got. So this is the introduction. So very basic level, network is a selection of nodes which are something like this, joined by edges. Now, ordinarily, we won't see this situation where you've got multiple edges, but just for this problem, there will. So this theory, the graph theory, began with what's called the bridges of Konigsberg problem. So find a route through this city, crossing every bridge exactly once. Now, what I'll have to do is, it's kind of hard to see the bridges here, so I'll have to color them in for you to see. So there's a bridge here. There's a bridge here, and I want to get this right. Seems to be a bridge here, and if I get this wrong, it'll mess it up. Okay, I think I have most of it. So there's a bridge here anyway. You know, I'm going to Google it just to get, so I can see it. The image doesn't come out very well. Sorry about this now. And unfortunately, I can't pause what I have. Here we go. There's another one there. Is that it? Oh no, there's another one there. Is that it? 1, 2, 3, 4, 5, 6, 7 bridges. 1, 2, 3, 4, 5. Okay, here we go. So the question is, can you find a route through the city? You don't have to start and end at the same place. Can you find a route through this that uses every bridge exactly once? So for example, maybe I'll go over here, 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 and then, well, if I go this way, I can't go on that bridge, and if I go this way, I can't go on that bridge, so that didn't work. So there's loads of different possibilities, but can you find a way that goes through each and every one exactly once? So my recommendation at this point is to pause the video and try and see, can you find such a route? Okay, now that we're back, so we're going to maybe just go through the hints. So the easier problem would be to replace the islands and the bridges using these nodes. So let's see, are we sure that these are the same thing? Perhaps not. I don't think these are the same picture. Oh no, this is an easier problem. Yeah, I was looking at this and I was like, how's... Okay, so this is an easier problem. So can we find a way around this? So, okay, so say we start here and go from here to here, and then we go from here to here, here to here, and here to here, and then here to... and that works. Okay, so let's maybe label the nodes and maybe write down what we did. So A, B, C, D. So we can get a route, and this is the notation that we'll eventually use. So A to B, then B to C, then back to B, then back to C, and then to D, and then back to A. Now I don't have to come back to the starting point here, I just have to use all the edges, but it just this way works. So A, B, C, B, C, D, A. That used every single edge. Look, I'll even number them here. So first we use that, then that, then that, then that, then that, and then that. Okay. So does this shed any light on this problem? Not necessarily. This was just supposed to be a hint. I mean, does this shed any light for you? We'll say nothing at the moment. Okay. So now let's consider this problem. So this seems to be a different problem. Can we go through this using every bridge exactly once? So if we're going to use this edge, whether we start here or finish here, we have to use this edge. And if we finish here, we can just go backwards. So let's call this A, B, C, D. So if we start at A and we go to B, and once we go to C, there's two options. We can't go to D because we can't use one of these edges, and if we use one of these edges, we can't get to D. So no matter what, whether you go to B or D, you're stuck. So this one, it's impossible. Now, are you completely convinced of that? Maybe we'll start again. So let's say if there is a walk through this, at some stage you'll get to A. Now, once you visit A, you can't come back because you're only going over the bridge once. You can't go back on the bridge. So once you visit A, you never come back. So either you start at A or end at A. If you end at A, run it backwards, and that's the same as starting at A. So start at A, you have to go to B. From B, you have to go to C, and then there's two options. Either you go back to B or you go back to D, and in either case, you're stuck. If you go back to B, you can't get back to C and down to D. If you go to D, you can't get back to C to use the one of these two edges that you didn't use. So this one is impossible. Now, is there anything here? Maybe, maybe not. Okay. So now what we're going to do is we're going to look at the original islands and replace them by nodes and edges. So maybe just to show that these are the same thing, I think what we're going to do is we're going to name, it's kind of the same. So we'll just number them. We'll call them A, B, C, D. So this is A, B, C, D. And if we go back here, that's A, B, C, D. And just to make sure these are the same, yeah, they're the same. So we're just replacing it down to basically its bare bones. Now, can we find one that goes through this? So let's see. Okay, if you started, okay, let's say, if you got a route, at some stage it's going to have to go to D, maybe. So starting at D, let's go to B. And actually, I'm not going to go through this. So there's loads of different possibilities. So what you could actually do is program all the possible routes. So for example, you could try D to B or D to A, and then just kind of look at all the possibilities. So after B, you could go to A or you could go to C. After A, you could go back to D, you could go to B, or you could go to C, and you could look at all these possibilities. And what you could do is, the problem is, like, maybe you don't start and end at D. Like, who knows? Now, the one thing you'd say is D and C look the same. So either start at D or A or B. And what you could do is just kind of do these kind of diagrams. Look, this is probably called a case-by-case analysis. And I think starting at D, look at all the cases. Start at A, look at all the cases. Start at B, look at all the cases. And no matter how you do it, I think you're going to get into trouble. Okay, and very shortly we will explain where the trouble comes from. If you've paused it and again, you can pause it and see if you can do it. And if you do, that's great. Okay, so now let's look at this one. So here, let me see, what am I going to do here? Okay, I'll start here, and I'll go from here to here, to here, to here, to here, to here, to here, to here. And I think that actually worked. So I need to put, if I want to write that down, I need some notation. So let's name the labels, or the nodes. A, B, C, D, E, and that's it. So I'm saying, let's go, let's see, does this work? And maybe I'll just put a red mark when I use them, and hopefully I get it right the first time. A to B to C to to E, to D to C, and then from C go to A, and then up to E, and then down to B. So it is possible here. Now, I think at this stage I probably have to kind of give the explainer. So the thing is, say you're at A. Because A has 3 edges. Now I'm going to introduce some vocabulary that we're going to use later. The number of edges that hit a node is going to be called the degree. So the degree of A is equal to 3. Now, because A has an odd number of edges, you can't start and finish there. So what I mean by this is, if I leave at an edge and come back, if I am to use every edge, if I leave, say, one of the edges, I come back one of the edges, there's one edge left over that I have to leave and I can never come back. So I can't start and end at A. Similarly with B, I can't start and end at B because it's got an odd degree. Say if I start at B and I leave it and I come back via another edge, I have to leave it again. Now, could I possibly start, say, at E, D, or C and go through B? So is that possible? So starting at D, E, or C and go through B. So we're going to see that that isn't possible either, because say you start at D, whatever, the first time you come to B, you will leave it, but eventually you have to come back. And there isn't a 4th edge to leave you go. So because it's odd, you can't go in there in the middle, because every time you visit it and you leave it, you can visit, leave, visit, but you can't leave again because there's only 3 edges. Whereas you can with E, because there's an even number of edges. You can visit E and leave it. Say visit, and let's see where we did it here. So we visited once, then we left, and we visited then from A, and then we left. So E can take place in the middle, but B can't. So what we've actually got down to here is, I think we said we can't start and end at A, we can't start and end at B, we can't have no A or B, A not being the start or the end. So A and B have to be the start and the end. That's what we've kind of said here. And what we can do is, and it's probably a lot of work to show it, is that starting and ending at A and B, okay, fine. Once you visit E, you can leave it, and every time you visit it, you can leave it again because there's an even number of edges. Okay, so let's see. Imagine that. Well, we'll go back to this one now, actually. So let's look at the degrees of each of these nodes. So you got the degree of A, the degree of B, the degree of C, degree of D, and finally the degree of E. So A has got 1, 2, 3, 4, 5. B has got 1, 2, 3. C has got 1, 2, 3. D has got 1, 2, 3. And E has got, there is no E. So you can't actually go around every single bridge, because, like, say you start and end at A and B, and it doesn't matter what pair you use here. So say you start and end at A and B. You visit D, you leave it. If you come back, because there's not an even, you can't leave it again. So we'll see it here. So say you start and end at A and B. So you start at A, you can visit D and leave it. And if you visit D again, so that's visit is the first edge, first part of the first edge, leave on the second edge. But then when you visit it again, it's on the 3rd edge, and there's no 4th edge to leave. So it's impossible actually to walk around this. And this was the beginning of this subject of graph theory. And what we've done here is a bit difficult, but it's just an introduction to the subject. So see, can we write down something? Except for the first and last nodes, for example, we might look at the degrees in the other graphs that we looked at. So in this one, we've got ABC, so degree of A, degree of B, degree of C, degree of D. And we don't want to write, by the way, A equals, so that's not very good math. So 2, B is 4, C is 4, and D is 2. So that one is fine, because they're all even. Now if 2 of them are odd, that's fine, because they can be the first and the last. Let's see here. So this time I'll just label the degrees 1, 1, 2, 3, 3, 3. And this one was impossible for the same reason. But this one was okay because we had 2 nodes of odd degree, but the rest of them are even. This one has degree 2, this one has degree 4, 4 edges, this one has degree 4. So you want 2 nodes of odd degree and the rest even, or all even. So except for the first and last nodes, every time the root visits a node via an edge, another edge must leave. Because say you visit E, you must leave it again. Now you can visit it multiple times, but every time you must leave it. So for every one in, there must be one out. So the degree must be even. Therefore, except for 2 nodes, every node must have an even number of edges. Okay, so that's a thing. I'm going to look at this a bit later on in this chapter. Okay, now let's see. So from what you've learned in task 1, write down a theorem about such roots. We use language with nodes of edges. So come up with a term that describes, to describe a root. Come up with a term to describe a root that visits every edge exactly once, such as this root visits every edge exactly once. Come up with a term to describe how many edges hit a node. Now, we may as well give it. It turns out that the barrier to solving the bridges of Konigsberg, that you have more than 2 nodes of odd degree, is a barrier for all networks. Turns out is the only barrier. That is, whenever this barrier does not exist, there is always a route through all edges that uses an edge only once. The proof of this is beyond the scope of the course. Well, yeah, I think what we're going to do is we're going to say that there is an algorithm, and you know, you can look up a textbook that shows that the algorithm always works. So what have we got? I'm going to give you the precise terminology. If you want to pause it and come up with your own, that's fine. But I'm going to go with this. A network has an Euler circuit. I have to get the right terminology. Yeah, an Euler circuit if and only if there are 0 or 2 nodes of odd degree. If you have 0 nodes of odd degree, you can make a loop that is starting and ending at the same place. Okay. Now, this graphs 1 to 10. I'm going to have to produce this. I'm going to scan this at the weekend. So this will be an exercise for you. So you analyze the degrees of the nodes. Now, you must be connected. Obviously, if there's 2 components of the graph that aren't connected, so then you can't walk around them. We'll learn later on what connected means. Okay, so this is, okay, here we go. I've just written the same thing. Eulerian trail, I think it's circuit. We might have to come back to that a little later. Maybe I'll just check it now. Probably want to get it right, don't we? I think it's a circuit. There's all manner of different languages in this. Yeah, Euler circuit is what we want to use. Or is the circuit the one that starts and ends at the same place? Yeah, it is, sorry. Oh, look, it's very, the language is very annoying. Okay, yeah, sorry. It's trail and circuit. Euler trail, my bad, trail. If and only if there are 2 or 0 nodes of odd degree. We'll see that the degree is number ahead. If there are 0 nodes of odd degree, then there is an Euler circuit, which can start at end at any node. If there are 2 nodes of odd degree, then you can start at one of these nodes and finish at the other, using all the edges but not looping back to where you started. So that's like here. So 2 nodes of odd degree, you can start and finish at these. Okay, so let's give some basics. So that's kind of an introduction, really, just a bit of messing around. Now we'll kind of do it properly. So in section 1.41, properties relate. We saw a relation on a set gives rise to a directed graph or a digraph. Recall that a relation is a subset of S times S, so it's some ordered pairs. The digraph has each element of S represented by a node and each relationship XY in the relation represented by a directed edge. So you've seen networks before in the previous chapter is what I'm saying here. Note that it's possible to have loops, but it's not possible to have multiple directed edges. And that's because a relation is a subset and it's a set, and so you can't have duplication. So in a digraph, you won't have multiple edges. So that'll be something like in Twitter, you can't follow the same person with the same account in two different ways. And indeed, you can't follow yourself, but I won't worry about that. So let's see some examples. Now we've seen digraphs in chapter 1, so this is just actually a bit of revision, just we're probably using some stuff we've seen before. Okay, so let's draw this. So the vertex set is A, B, C, D, E, and these are the edges. So let's draw A, B, C, D, E. But we can ask these kind of questions in this section anyway. So A, B, C, D, E. And let's draw some edges. So you got A to A is a loop, A to B, A to C, A to E, B to A. So I can draw one back, or else I can make this a double edge. B to D, C to C, loop, C to E, D to D, D to E, and E to D, which makes this a double edge. So I might just count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I get, I don't know how to count this now, maybe moving across the page. So 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I got 12. Oh dear. A to A is there. A to B is there. A to C is there. A to E is there. B to A, yeah. B to D. C to C, yeah. C to E, yeah. D to D, yeah. Did I miscount this? D to E, E to D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, so okay, let's count all the edges. Okay, so if you're stuck here like I am, making a fool of yourself, what you can do is you can look at, you can kind of add up the degrees, I think. Oh, but the degrees aren't ideal there, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's 11 there. Okay, that's the digraph. The set E is a relation. Is this relation reflexive? So reflexive, if you remember, is everything is related to itself. So to answer this question, no. How can you see from the digraph? Not every node has a loop. So let's just say B. So no, you could say B or E. You don't really have to say both. No loop at B. To be reflexive, every single node must have a loop. Right, Winter 2017. List the elements of V and E, where V is the set of vertices and E is the set of edges of the graph represented below. So the V are the vertices, so it's a set. So I see P, Q, or ST. P, Q, or ST. And the edges. Now, as there's arrows, that means that order is important, so we use rounding brackets. So let's go P. So we've got P to R, P to T, P to S. So P to R, P to T, P to S. Let's go Q. Q to Q, and Q to S. Let's go R. So R is related to T, but the other arrows are incoming, so I won't list them. Let's go S. S is related to T. and finally T is related to R. So what's very important here is get the roundy brackets because order is important. Okay, so that's the real basics of this. I think that's probably enough to start on. We might just have a little look at the exercises for you. So consider V, A, B, A to E. Okay, the set of all vertices in the following graph. Define a relation R and V for any XY is related if there's a walk from X to Y with an even number of edges. So there's going to be a bit of work in this. So explain why R is reflexive, symmetric, transitive, and find the equivalence classes. So that's a good tough question to check out. Probably what you should do is make a new digraph. A, B, C, D, E, F, and maybe I'll just start you off here. And so things are related if there is a walk of with an even number of edges. So A is certainly related to itself because you can go A to E to A. Now can you go from A to B in 2? You can. A to E to B. Can you go from A to C in 2? Yes, you can. Can I go to A to D in 2? Now, a proof is probably difficult, but I think it's going to be impossible. So you can't go that way. Like if you go from there to there, you're going to, yeah, it's probably impossible. I mean, it doesn't seem to, well, I'm just drawing the digraph. So I go 1, 2, 3, 4, 5. 1, 2, 3. It seems whatever way I do it, I can't get to D. So there's no line from A to D. Similarly, none from A to E. What about F? 1, 2, 3. Similar story. We're not going to be able to get from. So that's start of A. So I'd recommend doing the rest for B, C, D, E, F. And from the digraph is probably the best way to analyze this. Considering write down a set of vertices and edges. Now I'm missing a little bit here. So it's good that I did this little bit. If it's undirected, then the order doesn't matter, use curly brackets. So this edge, for example, here. So if I call this, say, edge 1 you would write as edge from A to B, but use curly brackets. So have we got a graph on the next page? Yeah, this to be an E. This one, okay, you're going to form a relation and draw the digraph. In this one, similar story, and this one's probably a harder example.